Let's look at some properties of the wonderful and always present normal curve. Normal curve looks like this. It's a bell shape where you have this middle part here where a lot of the data is, and then as you go to the high extremes and to the low extremes, you'll find that most of your the amount of data in those areas trails off. And one thing about the normal curve that you'll get used to is this idea of how many standard deviations you are below the mean or above the mean. And those are all, of course, z-scores. So the z-scores can be used in any distribution, but one place that it comes up a lot is when you're using different measurements with the normal curve. Reason being is that every normal curve looks the same if you put your measurements in z-scores. So it allows you to have one standard normal curve that you do all of your measurements with. Quick refresher on z-score, it's the number of standard deviations from the mean, and to do that you take your value, whatever it is, you subtract the mean to see how far above or below the mean it is, and then you divide by the standard deviation to figure out how many standard deviations above or below the mean it is. So for example here, you're going to end up looking at the normal curve and you might have one standard deviation above, and that's going to occur right here. Now one thing that we don't ask when we're looking at the normal curve that we might ask if we're dealing with, let's say, a binomial probability is what is the probability that the z-score is exactly equal to 1? And that P of notation means the probability that z-score is equal to 1. And the reason is that the normal curve is a continuous distribution, which means that the difference between 1 and 1.000001 is infinitely tiny. It's all the values are effectively connected. So the probability that something has a z-score of exactly 1 in a perfect normal curve isn't really a logical question to ask because it's just an infinite slice. So what we do ask instead is the probability of being under a certain region. And if you look at the entire normal curve at once, the probability of being somewhere under there is 1.0. And 1.0 corresponds to 100%. There's a 100% chance that you are somewhere under the entire normal curve. And that's something you see with probability. All of the outcomes add up to 100%. But now let's just look at -1 to +1 standard deviations. 68%, 0.68 probability that you're going to end up in that region. So only getting one standard deviation in either direction is going to account for the majority of your data. Over 2/3 of your data is going to end up just in this one region here alone. So between -1 and 1 standard deviation. Next thing that you might go out to is all the way out to -2 or +2 standard deviation, and that area corresponds to 95%. Now one of the reasons that the -2 to 2 standard deviations is particularly common to talk about or think about is when you think about confidence intervals at 95% or hypothesis tests with a alpha value of 0.05 from two different tails, you're going to see this z-score of 2 or -2 come up quite a bit. So this is something we look at a lot. And then finally, once you go out to -3 and +3 standard deviations, you're talking with about 99.7% of all data. So if your data follows a normal distribution, the probability of being outside of those ±3 standard deviations is incredibly, incredibly low. And when they talk about things like Six Sigma in business, what they're talking about is keeping everything here within that +3 to -3 standard deviations in your factory processes. So the vast majority, only 0.3%, will be outside of that. So looking at that again real quick, we're going to see that we have 68% within 1 standard deviation, 95% within 2, 99.7% within 3 standard deviations. Another thing to think about is what happens if you accumulate everything at or below a certain point in the normal curve. And I'm going to jump back here for a second. If you take all of this area and add it up and graph it, and then you keep going and all of the area below any given point and graph it, what it's going to do is it's going to form an S-curve. And let's take a look at what that's like. Down at the very bottom here, we just graph what we have, and then we start to accumulate a little bit. So we have a little bit going into it, and now we're adding more faster because more data is in the middle. So we add more faster and faster and faster here. And then we stop having quite as much data. So then we slow down, slow down, slow down. So for those of you that have taken calculus, you're thinking of an integral. For the rest of us, we're just thinking about adding up all the area under the curve at or below any given point, and that's going to correspond to a point on this graph here. So this accumulating graph forms this S-curve. And what that can do is that can be applied to different areas studying business and product adoption and things like that.